So this is the final version of the heat transfer project code for that same thermal distribution. The code starts out the same: 0.2, 0.4, 0.6, 0.8 slip time seconds, time step of 5 thousandths, all the same material properties, all of the same basics. But you can even see, according to the slider, it's a much shorter code. And I'm kind of proud of how well I was able to condense it. So we still have the same flux, and all of the horizontal, vertical, conductive heat transfer surface areas, convective surface areas, flux surface areas, things like that. Um, they're all still, for the most part, untouched. The main difference between the two sets of code is that I went from using um, an array for each node within the mesh to creating, in this version, it creates a three-dimensional matrix where the x and y components of each array, or each two-dimensional array within the matrix, represents the radius and height values of the various nodes. And then the third dimension of that matrix represents those temperatures as a function of time. Um, and so those same 80 lines of code in the initial code have now been condensed to lines 44 through 52, and 52 itself actually doesn't do anything. Effectively, what it goes down to, and what the updated version does, is it uses a series of logic operators to find if a node is in the corner of the structure or if it's on one of the faces of the structure, and basically any of those conditions that are met changes the contributions that are enacted on that node by any of the other nodes or external conditions, particularly with the flux. So all of the rest of this bottom part is roughly the same. It's been updated a bit to where it just refines the output so that it looks a bit more professional. So you can see, first of all, it responds a bit faster. Second of all, in the temperature distribution plots, the code now finds the critical, max temperature differential at any given point. It responds with the time value where that discrepancy occurs, or not discrepancy, but difference occurs, and it outputs the actual value of that temperature difference for each of the 4 slip times. Other than that, the tiling of each output is still the same. As I stated in the last video, and as you can see in this one, in addition to changing the orientation of the three-dimensional output, I was able to fix the code, and so now this top surface flux acts appropriately to where this outermost corner node is substantially hotter than its companions, I guess, by the end of each trial. So it just runs a bit better. It's more efficient. The code is much shorter, and so for troubleshooting purposes, when I created this, it actually took me far less time to troubleshoot the code once I had it typed out. The rough version of the code, I probably typed it in 4 days, and then in addition to the troubleshooting that was done as I was creating it, it required an extra 2 days of troubleshooting just because of how much raw code there was. This one, without including the troubleshooting that I did as I was writing the code, it probably took me 6 hours to troubleshoot. Now granted, that was also accounting for the fact that I didn't have to retype any of the bar conditions. So this section of code right here is what changes the color of each bar, which is why they change color. Well, as you can see by that portion. Also, this section, if it's taken out and you rerun the code, just gives kind of a different look to it. It's one of those things where I was wanting to have some fun with it. But all in all, this is the final version of my heat transfer project code, and I'm pretty proud of it, just because, you know,